on ceramic filter materials at high temperature to determine their mechanical properties. So ceramic filter materials are used for infiltration of metal melts such as steel and aluminum, and they have proven their efficient performance on the final product. But during this, their service life, they bear considerable thermal and mechanic loads, which makes it crucial to understand their mechanical properties, especially at higher temperatures. So in this picture, you can see an open cell filter made from carbon bonded aluminum. This material has been researched in our Collaborative Research Center 920 in Freiberg for the last 10 years from different aspects, and on top of that, recently there are new attempts to alternate to replace the hazardous carbon content of carbon bonded alumina with environmentally friendly lactose and tannin binder systems. And my talk is based on comparison of this carbon bonded alumina and two different lactose and tannin based carbon bonded alumina with different lactose to tannin ratios. So I used precision disk test in this work, and it is a well established kind of old test which compresses the specimen, and this compressive forces cause indirect tensile stresses along the vertical axis of the specimen, which splits the disc to two halves, and the Brazilian tensile strength is the factor of the specimen radius, thickness, and the final load at which it breaks. As it seems easy to interpret for stiff materials like granite or concrete, in case of filter materials, due to its pore structure, it's not the case. So there are more complications to that. Therefore, at first I wanted to study the different test variations, and by adjusting the specimen geometry or the punch geometry. So you can see here 5 different variations with flat punches and curved punches applied on the round specimen, and then a flattened specimen on the contact point compressed by a flat punch, and 2 other specimens with different aperture ratios of the hole to diameter ratio compressed with flat punches. So to begin with, I used a digital image correlation using Aramis adjustable system to obtain a displacement map throughout the test, and which gives me this contour plot from the experiment, which later I introduced this data to my simulations so that I can do a parameter identification. So also you can note that there is this plastically deformed part at the contact region of the round specimen. So here what I did, for example, to just do my simulations with elastic parameters, I was able to collect my displacement in y direction only below the plastically deformed region, and later I made my numerical simulations using finite element method and in Abacus software, and the force data from the experiment was used as a boundary condition for these models, and the rest was to do a reverse material parameter identification to bring the displacement curves, force displacement curves of the simulation closer to the experiments, and this gave me elastic properties of the material and tensile strength of the carbon bonded alumina at room temperature. And so I didn't went to too much detail into this work. There has been a publication regarding this work. And recently, another colleague from our collaborative research center from another department made experimental work on these three and some other variations of these filter materials, and obtained elastic modulus, tensile strength, and the crushing strength, which is the compressive strength of the material. A cylindrical specimen, compressed, and I used these parameters later for my simulations. I will come to that point in a bit. So this is my test setup. You can see the first of all, it's because it's inside the oven, it's closed, so there's no access to the surface of the specimen. And you may also notice that due to the thick isolation layers, I need to use long displacement ceramic parts to be applied to be able to apply my forces on the specimen inside the oven. So the takeover from my previous study was that I need to use the variation with a hole inside, first to decrease the forces that it faces, so therefore I can minimize the displacement of my test setup, the whole thing. And also the second thing was, and the most important one, was the predictability of the crack path, which will bring me to my applied modeling. And by the way, also in order to prevent the oxidation of the carbon bonded alumina, the carbon inside the material, the argon gas has been flows here to make a protective, neutral environment. And by the way, I also made this specimens a little bit smaller to decrease my loads. And the test temperature was 1200. So I talked about the predictability of the crack path, so which is the main criteria for application of the cohesive zone model. And so I modeled my cohesive elements along the vertical diameter of the model, and then you can see also the formed stresses around the tip of the hole. I used bilinear cohesive law for my model, and therefore assuming that the tractional stresses are the stresses that cause to the failure of the material. And from here. So these are my experimental results. You can see three different typical curves for the force values that cause the failure of the three different materials. And before doing the specimen with the hole inside, I did the intact specimens, and they had much bigger scatter in the results. So this variation of the test was also good with the accuracy and repeatability of the test results. And later, by adjusting the parameters, the cohesive parameters, I was able to fit my simulation data to the experimental data, and doing that, I obtained the elastic modulus, tensile strength, and crushing strength. So you see that there's a drop in elastic modulus and increase in tensile and crushing strength of the material at 1200 degrees Celsius in comparison to room temperature. So the conclusions from this work is that although I didn't have accurate Y displacement information data from my experiment, I was able to use cohesive zone model to find out the tensile strength of my filter materials first of all, and there's a considerable increase in tensile strength of the filter materials at higher temperatures, and it's also obvious that lactose and tannin-based binder systems cannot provide a comparable properties to that of carbon bonded alumina, even at high temperature as it is in the room temperature. So from here I could apply, I could increase my sample number to get a better distribution of the failure loads for the Brazilian disk test, and therefore apply the Weibull theory to get a failure likelihood of my specimens first of all, and then as you can see in this picture, so there is the first crack formed along the vertical axis, and then there are secondary cracks forming from starting from the contact point. So would be interesting to apply phase field model to predict the sequence of these cracks and the direction they are growing to. And finally, I would like to acknowledge the support of German Research Foundation under the framework of Collaborative Research Center 920, and here are my contact details if you would like to do some collaboration, and I thank you for your attention.
Thank you for a very nice talk. So now we have time for some questions. Yes, please.
If I understood, you use GIC at room temperature,
Yes.
but not at high temperature.
That's right.
Okay. How do you compare the displacement at room temperature between the displacement and the displacement by the machine and the displacement by GIC?
Yes, that's right. That's right.
You have seen difference between these two experimental data, so by just the displacement and the displacement by GIC? That was the reason actually I used it. I shifted my attention to the IC because I always noticed so the deformation, the displacement I get from my test result includes also the deformed area under the contact point. So that was not accurate data. So there is almost 5 to 6 times difference between the displacement from DIC and the contact data, and that's only because of the contact point process. So probably you have the same problem at high temperature. No?
That's right.
Okay, so how do you modify your displacement in order to have a good correlation? Because when you present the correlation between experimental test and numerical results, this works. It works.
Yeah. So,
but it seems a little bit strange because you don't have the good displacement.
Yes. At high temperature, as I mentioned, I don't have accurate displacement data, so I only used the force value as my boundary condition. Okay. And yeah, maybe it could be interesting to get an oven with a transparent surface to get a displacement map and see that. And one of the other attempts I made was to create this stress concentration factor at the tip of the hole, so that to some extent, I decreased the displacement at the contact point. But then the other problem is the displacement of the test setup comes to, and that's basically impossible to obtain. So the test setup is also ceramic parts, and they are also very deformable, especially at high temperatures. So displacement, I guess, would stay a mystery.
Another question? Yes, please.
I think you, as far as you understood, you don't know your real coalition parameters. How can you then be sure that your result is correct or unique or
Well, actually, so these are here obtained from the experimental data. And I took them as my cohesive parameters. So especially the tensile strength value.
yeah, but you don't know you don't know the cohesive energy, right?
Yes, for that there has been also other works on the same material using different tests, like chevron notch test, for example. So starting with these assumptions, I already had a good assumption to start with, which is also obtained from the same material. But I also, when I just took the displacement as my damage criteria, displacement of the cohesive elements, then I also didn't get too far from my results.
I just wanted to make a comment about this measure problem of measurement at high temperatures. So of course, we have all this deformation of the ceramic loading parts and all this stuff. We had similar, not a problem, but we used only 4-point bending, and then obviously what we had were very fine or thin rods, ceramic rods, which were going out of the oven, of the furnace. Sorry. So this gave us a real displacement in the center. But in this case, it is probably more difficult. But still, maybe it can be somehow calibrated. I don't know. That you would know actually how your rods deform at high temperatures. Then you can subtract it maybe.
Yeah, that's a very valuable comment. I will definitely investigate on that.
Yeah. Okay. Any other questions? If not, thank you very much.